Welcome to the ANP Sensitivity Workshop with Bill Adams. Thank you, Bill, again for accepting to do this workshop. Floor is all yours.
Excellent. All right. Well, welcome to this ANP Sensitivity Workshop. My name is Dr. Bill Adams, but I go by Bill. If you have any questions during the presentation, I'll stop periodically and ask. You can raise a hand as well, or just ask me. I'll be happy to entertain any questions you have. So, let me get over here. So ANP sensitivity, the superpower. Well, what do I mean by that? So ANP Row Sensitivity is something I developed, I don't know, 12 years ago now, something like that, to solve a very specific problem, but it turns out it has a lot of applications elsewhere. So why is it a superpower? Well, with it, you can do a lot of interesting things. You can effectively shape public opinion using influence and marginal analysis. I'll go through a little bit more of this details in a minute, but I just want to kind of give you an overview. If you have a good model, you can use this to try and change public opinion on things. You can also find the most influential parts of your model in general. So what's causing your alternatives to score the way they are? Not just what's the score and the rank, but why? What structure in your model? What parts cause that? You can use it to save time and everybody's patience. We all know pairwise comparisons can be insanely tedious. Using this, you could do a quick cursory pairwise comparison and use marginal analysis to find the right places to focus in on the more detailed parts. And I'll get into this again in a bit. You can understand the world from a single perspective. What if one node becomes the most important thing? How do your alternatives shake out in your model? So you can do this in AHP very easily, but ANP without row sensitivity, that's not possible. It also helps you understand where to focus your attention. So if all you really care about is rank changes, then little influences that cause scores to go up or down aren't particularly interesting. What's more interesting is what causes a rank change, and we can do that as well. So today I got 5 topics I'd like to cover. We've sort of talked a little bit about this, but we'll go into more detail about why it's important. I'd like to discuss the ideas behind row sensitivity, how it was created, why it was created, and why it behaves the way it does. I'd like to give you a detailed view, some details on the calculation so you can understand how to do it yourself, but there are libraries out there that do it, and I'll talk about those. So you don't have to do the calculations yourself. We'll go into some more of these applications that I've sort of outlined in the beginning here. And then I'll give you a glimpse of how to use my PyANP library, which is a Python library, to do some of these calculations. Okay. So any questions before I move on? Excuse me. All right. So let's start off with why is it so important? And I kind of gave you an overview of why it's important. It can be used in lots of situations. The idea of shaping public opinion actually came from Tom Soddy whenever he saw my first presentation on this in the question and answer session afterwards. He said, Bill, could you do this with that calculation? And I said, in fact, you could. I never thought of it that way, though. But he always had a good idea of how to apply a calculation to get something accomplished. You can find the most influential parts, the saving time and everyone's patience. I don't know of anybody who's used it for this yet, but it definitely could be used for that. Perspective analysis and rank analysis. So it's important. It's very useful. It can do a lot of cool things. So let's go into this a little bit deeper just on each one of them. So if you're modeling for instance, if you're modeling public preference to do or not do an environmental reform, and you find out that people don't want to do it, how can you try to make the public understand that it's important? How can you effectively show people that this reform is necessary? With marginal analysis, if you have a good model set up, you can find the criteria that has the most immediate impact on making don't do it more or do it more important, and try to change public opinion on that criteria. So you know where to change to attempt to adjust public opinion in order to make your desired outcome happen. So that's the first idea. Questions on that? No? The general application on any model, influence analysis allows us to find out which node/criterion affects the alternative scores most. And by how much? In which way? Does it affect it up or down on particular alternatives? We can either do small changes. What happens if this node is a little bit more important? What happens if it's a lot more important? And to see how it affects how your alternatives shake out. This one, make everybody less crazy going through a pairwise comparison. You can start with just doing a cursory pairwise comparison, maybe just doing the off-diagonal ones, just a bare minimum set to get started for all of the pairwise that you have to do. And then if you do a marginal analysis, what that's going to tell you is which nodes have the most impact on the score. So there may be a place that has essentially no impact at all. And so why bother pairwise comparing those things to death when it doesn't matter. So if instead you just do a cursory comparison and then find the places that really have an impact, and then you can do a deep dive pairwise comparison on the ones that have the most impact. So you can save a lot of time and effort for people if you use this pattern. Any questions on that? All right. Understanding the world from a single perspective. So if you have a whole bunch of criteria, the question could come up, the idea for this is, how important are the alternatives with respect to one criteria? If that criteria was the only one in existence, but the whole model still existed, how would the alternatives shake out? So what you're doing there is essentially saying that node that you're interested in, let's say, I don't know, public service is a node. If public service becomes the most important, how do the alternative scores shake out? It turns out in an ANP model, because of the feedback, it's not just the local priorities in the column there from the supermatrix. It's more subtle than that. But what it does tell you is, what does the world look like if that is the most important criteria in the model? So from the perspective of that criterion, what would the alternative shake out as? And lastly, for where to focus our attention. Again, for any ANP model, generally what you care about at the end are rankings. And so if that's the case, you want to focus on the criteria that most quickly cause a rank change, because that's the place that gives you some interesting behavior. So rank analysis is a calculation I developed that does just that. It finds which nodes have, essentially what it does is it finds how much do you have to change the priority of a node in order to get a rank change. Questions? All right, so why did I create ANP row sensitivity or ANP sensitivity? There's already an AHP calculation out there. Why didn't I just use that? Well, in fact, I did. And it turns out it's completely ineffective for a general ANP model. The AHP sensitivity, that method effectively changes one cell in a matrix. So your super matrix has the number of nodes by the number of nodes entries, so nodes squared. You're changing only one entry in that. This works in the case of AHP models because most of that super matrix is zeros. So one cell can make a huge difference in those cases, some cases. Generally, it's the ones towards the top of your tree or top of your hierarchy that have the real strong impact. But in ANP models, a single entry has essentially no effect. There's just no sensitivity. So how can I possibly fix that? Because there is sensitivity going on in here. So just a refresher on how AHP sensitivity in a hierarchy or even a tree setting looks. It changes essentially the local priority. So you've got your tree there, and it just changes the local weight of a criteria and rebalances on the rest. It changes the local priority from 0 to 1. There's also a global version of it to do where you can change the global priority. So this idea that you have a node and you're wanting to change how important that node is very straightforward in the AHP tree view. It's also pretty straightforward in the hierarchy view. But in the supermatrix view, remember, I have to talk about an entry, which is a row and a column. So it's not just a node, it's a node with respect to another node. The real AHP version is really talking about changing the importance of a node. And that's what I pivoted on when I developed this. So here's the naive idea. First, I want to mimic the AHP version as much as possible. In particular, this idea of changing how important a node criteria in a model is from 0 to 1. 0 means it's completely unimportant. 1 means it's the most important thing in the world in this model. So, and since the supermatrix is where all of this information lives in ANP world, then I should be playing around in that place. I want to make the priority of the node go down towards 0. I want to be able to make it go scale down. And I also want to have the capability of scaling it upwards. There's two different cases here. The math works out slightly different in both. Okay, let me get to the axiomatic rules and I'll stop for questions. So the naive idea is I'm mimicking AHP by changing the priority of a node either upwards or downwards towards 0 or 1. Okay, so the axiomatic rules, the rules I came up with for this. One is we only change the supermatrix. That's how we're going to make these adjustments. Second, there's a parameter P, I call it P, that is between 0 and 1. That's going to specify how much I change the priority of this node. As P goes to 0, the resulting priority of that node should go towards 0. In other words, once I take the supermatrix, scale it maybe, and then do the limit matrix, as I push P to 0, that node's priority that comes out from the limit matrix should go to 0. And as I push P up towards 1, the node's priority should go towards 1. And then there's between 0 and 1, there's a value somewhere in the middle. Doesn't have to be exactly in the middle, but some value, P0, which is go back to where I started. And I want to keep as many ratios as possible the same in the supermatrix. So ANP is all about ratios. AHP and ANP is all about ratios. The supermatrix is all about ratios. So I'm going to have to break ratios a little bit to change the supermatrix. But I want to break them as little as possible. Note that rule 2 is really just saying, it's my way of saying this new creation is going to have to behave like the AHP version. All right, so before I continue, I forgot to mention one part here, which is sort of the most important part. The way we do this, and we'll see it in specifics, is we change a row in the supermatrix. Rather than changing one entry, which is the old AHP version, we change the entire row for that node. That's why it's called row sensitivity. In such a way as to make these axioms follow. All right, any questions before I move on? No? Okay, so again, remember, we're doing these calculations effectively so we can do a deeper analysis of our model. So I'm going to go into the details of the calculation. The calculation is not all that hard, but it has a little tedium to it. So first, remember I told you there are two cases, trying to scale it downward and scaling it upward. So we're going to handle scaling downward. P0, remember, is our resting value. It's everything's back to normal. So if I'm trying to slide it downward, I'm going to take the row and scale it down by the ratio of P over P0. In other words, I'm going to scale it down, multiply it by a number between 0 and 1, which is what this P over P0 is. And then once I've changed this row, my columns no longer add to 1. So column by column, I'm going to leave this row number unchanged and change the rest of the columns values so that it still adds to 1. I'll deal with the bigger case later. So we're going to spend a little time here. So I have this resting P0 value right here. What about that? It can have many values. It's your choice. Okay. There's the smart P0, which I can't get into with our time constraints here. It's the thing that makes everything work out as nicely as possible. That's why it's called smart. You could take the global priority. So once you have your super matrix, you could take the global priority vector and just use whatever the global priority of your node is for each node as the P0. So each node would have a slightly different one. Or the easiest thing to do is just say 1/2. Every node, the resting value is 1/2. So if you do a P less than 1/2, you're scaling down. If you do P bigger than 1/2, you're scaling up. That's what I'm going to do when I show the calculation here, but you can choose other ones. So for this, I'm going to choose P0 equals 1/2 for the calculations I show you. Smart P0 is generally the best choice though. So like in super decisions or in my ANP library, when you don't have to do the calculations yourself and software does them for you, Smart P0 will make graphs look nice. It makes everything work out well. So P0 is this resting value. So P is for our row. How much am I scaling it upwards or downwards? And P0 tells me where I break the line from scaling down to scaling up. Questions? All right. Grab a sip of coffee. Okay. So for all of the calculations I'm going to show you here, we're going to have 5. The model has 5 nodes in it. There are 3 criteria and 2 alternatives. I didn't try to make this interesting. I tried to make it as easy to calculate as possible. So that's why it looks like this. And the network is fully connected, just to make life easy for us. And the super matrix looks like this. So I put my criteria first and my alternatives at the end. You can see that it's fully connected. I've got all of these, none of the values are 0 in any of them. The limit matrix that comes out of this looks like the following. And then if you take that limit matrix, pull out the alt1 and alt2 and rescale them, you get these scores. So alt1 loses, alt2 wins. Okay, so this is the model. Again, it's just a toy model for demonstration purposes to make the calculations easy.
Yeah, could you explain these alt scores again?
Yes, so A1 and A2 are my alternatives. Here's my super matrix. When I calculate the limit matrix, each column here is my global priority vector. And so in particular, my global priority of alt1 is 0.098. For alt2 is 0.0152. If I take those two numbers and rescale them to add up to 1, that's what gives me the alt scores.
Thank you. Thank you.
You're welcome. Did that clear it up?
Yes.
Okay. Any other questions? All right. So the first calculation, scaling down. So remember, I haven't even talked about how we're going to scale up yet. So we're scaling down. I'm going to work on row 2, node 2. And remember I said P0, my resting value is going to be 1/2. And I'm going to go use P as a fourth, and I'll show you why that's what I did here in just a second. So when I use P as a fourth and my resting value is at a half, 1/4 divided by a half is 1/2. So in other words, I'm going to take my row and scale it down by a factor of a half for this calculation. So that row in the matrix there that's outlined in red, I'm going to scale it down by a half. And that results in this new row. So I didn't just change one entry here. I changed the entire row. By the way, when I'm sharing, do you guys see my mouse moving as I'm trying to point or no? Yes?
Yes. Yes.
Okay. Okay, good. Want to make sure that was, as I'm trying to use that to point. Excellent. Okay, so I didn't just change one entry, I changed the entire row here, which is good. That's what I'm trying to do. I'm scaling it down, making it less important. Now that I've done this, my columns no longer add up to 1. And so that's the next phase of the game, is I have to make my column add up to 1. So let's work on the first column. It originally added up to 0.76 because originally this entry is 0.24, so everything else added up to 0.76 to make this column. Add to 1. Now it needs to add to 0.88 because the rest of the column, the new value is a 0.12. So I have to multiply by 0.88 over 0.76. So I'm taking these values here and multiplying by 0.88 over 0.76 for each one of them. And after I do that, I get this new results. Notice they're bigger, right? 0.48 went to 0.55, 0.08 went to 0.09, which makes sense. They have to total up to something bigger. Now, notice that the ratios of all of these are still the same after this. The only ratio that got broken was this middle values ratio. So I'm respecting ratios as much as humanly possible while still making changes. Okay, so I changed the row first. Now I'm changing this column, so it's a column that adds up to 1. Questions? All right. Do the same thing for the second column. The second column originally added to 0.84 because this was a 0.16. Now it needs to add to 0.92. I do the same kind of multiplication to rescale. And now it's scaled up again. This was 0.16, it's now 0.17, 0.48 to 0.52, etc. And so now my second column adds to 1. And the same for the third column. It originally had to add to 0.72. And now since the new value here is 0.14, I got to make the rest of them add up to 0.86. So, whoops, I have the wrong number there. Where is the wrong number at? Yes, I've got the wrong numbers here, but it does work out correctly here. I typed in the wrong numbers here, but it actually adds up to the right one there. I need to fix that. Excuse me while I make a note. Fix. All right. And so on, you do the same thing for the fourth column. This went from 0.18 to 0.09, so I have to make the rest of these add up correctly. The rest of them have to add up to 0.91. So I change the other 4 entries there and do it on the fifth column as well. And so before I had a row that looked like this. after I've scaled this row down by a half and rescaled each column's values so that they add up to 1. Questions? And then what you would do after this point is take the limit matrix. So there's the limit matrix before. Here's the limit matrix afterwards. So my alternative scores went from being 0.392 to 0.6695. Conclusions, it's not a lot of change, right? Certainly didn't get any rank reversal, didn't have much change. That's not unusual for scaling down. So if you think about it, if you have, let's say you have 10 nodes, every node is about 1/10 on average of weight. So it doesn't have a lot of room to move down. Even if I kind of stretch out that moving going slowly, it doesn't have a lot of room to move down, but it's got a ton of room to move upward. So that means that moving down is not going to have that much change because you don't really have a lot of room to move down. And that's what you're seeing here. Generally, moving down the importance isn't what's going to make you see lots of interesting stuff. It's when you move up. Okay, so all of this was talking about scaling down, which is half the problem. Scaling up is a little more subtle. And you'll see why in a second. I'm going to try and motivate why I do it this slightly more subtle way. Any questions about scaling down? And again, you don't actually have to do this yourself. If you have your model in super decisions, it has the calculation built in under row sensitivity. If you're using my Pi ANP module to do it, it's got row sensitivity built in to it as well. So you don't have to do these by hand. Okay, so let's move on to scaling upward. It's not the same. So let's just try naively. I scale down by multiplying by a half. So why don't I just scale up by multiplying the whole row? Why wouldn't I do that? The most I can do, the maximum value, let me go back real quick. The maximum value in this row is 0.028. In other words, the most I could multiply by would be 1 over 0.028. And when I do multiply my row by that, this entry turns to a 1, but the other ones don't quite go to 1 yet. So if I want to push the priority of this node all the way up to 1, I'm out of luck. I've pushed up somewhat closer, but not really. I'm still missing a lot of value here on this 0.57, this 0.642. It's not possible in a super matrix to push them any higher because I can't have a number bigger than 1. I couldn't multiply by, let's say, 10, for instance, in this, because I'd wind up with a bunch of numbers bigger than 1. So the row hasn't been pushed towards 1, but I can't by multiplying the row by just a constant factor. So that's why I do something different, because the first naive approach doesn't work. Because of our axioms. Remember the axiom I had that was really important, that is, as I push P towards 1, I want the resulting priority for my node to go to 1, which means I have to have the row go to 1. And that's not happening if I do this naive approach. So I got to do something else. All right, so instead of scaling, just multiplying, what I'm going to do is scale down how far each entry is away from 1 by a number. So, and it's easier to see this once I do an example. So it's the same basic idea. Make a change to the row and then make the columns add up to 1. Same formula there. It's just I got to do something a little different on my row. So let's actually go through this example, an example here, just changing the row, and then let me see if you have questions. So same model, same end to row, same P0, and now I'm going to go scale up to 3/4, which effectively means I'm going to half the distance. That's why I chose 3/4. Just like the first one I chose it, so it would scale it down by a half. Now I'm going to scale the distance from 1 by a half. So let's do the calculation. So given this row, each element's distance from 1 is the following. 0.24 is 0.76 away from 1. 0.16 is 0.84 distance from 1. 0.28 is 0.72 distance from 1. So if I take this thing, these distances, and half them, I get this. So just halving each of these distances. So these numbers are half the distance from 1 that these numbers were. 0.24 was a 0.76 away from 1. 0.62 is a 0.38 from 1. So each one of these numbers is half the distance from 1 that these are. The reason I'm scaling down the distance from 1 is so I can push my row steadily towards 1. So after I've made this change, notice huge change, right? Went from 0.24 to 0.68, or sorry, 0.62. Big change. So scaling down, smaller change. It had a smaller effect. Scaling upward by a factor of half, much bigger change. And now you can see my columns definitely don't add up to 1 anymore, so I have to update the columns. All right. Any questions on this scaling upward? So it's just scaling down the distance from 1 for each entry. The scaling of the columns is easy. The rest of the column has to add up to 1 minus the value of row 2. So now they just need to add up to 1/2 of that. So they just have to add up to half as much. So I just need to multiply each column by a half, except for the values I changed, just half them. So these values in the red box, I'm just going to multiply by a half. And that makes my columns add up to 1 now. So whatever I scaled this distance away from 1 by is the same thing I'm going to multiply the rest of the elements by. And that makes the matrix work out. Okay. So before, let me go back here again. So this is before. Actually, before was back over there. Anyways, this is the after super matrix. So let's see what the resulting changes are. So recall our priority scores were initially this. After making that change, we have a rank reversal. Alt 1 suddenly becomes the best, and Alt 2 is the worst, dramatically even. Can you guys hear me now? My microphone got
You can
changed.
hear now.
Okay.
But we lost you for several seconds.
Okay. Sorry about that. I think somebody in my house opened up a pair of AirPods and stole my microphone. So anyways, so we got a rank reversal here. Just by doing effectively the same kind of scaling by a half, but because we're scaling upwards, it has a huge impact. So scaling upwards often has this impact. Scaling downwards almost never does. Scaling upwards almost always has some impact, at least for influential criteria. Now, there are criteria, every model, just to give you guys kind of a rule of thumb I've seen, about 20% of the nodes have significant influence. And then there's a little range of middle influence, and then well over half, typically 3/4 of the nodes have essentially no influence. It's very strange for fully connected networks, I should say. Okay. So for applications, we had these 4 applications plus the other one about the changing public opinion. So I'm just going to do another review of the influence analysis. So for influence analysis, the way we typically do the calculation, you use P0 as a half. It's the easiest one to use. You can use smart P0 if you want. Pick some P for this particular method using P0 a half works really well. Pick a P downward to use and a P upward to use. Typically, the default in super decisions, for instance, is 1/4 and 3/4, which are the numbers we were just using in this example. And then you look at how much the resulting priority scores change for each node. And so you have, for each node, you'll have a delta between the priority scores or the alternative scores. Mostly you'll want the alternative scores. And then you just look at the nodes that happen to give the largest change. So that's how influence analysis works. So again, for influence analysis, you use P0 as a half. You have a downward push that you do, an upward push, and you look and see which node has the most impact on your alternatives. You could do this analysis and just say which nodes have the most impact on a specific alternative or across the board. It's up to you how you want to do that analysis. And again, Super Decisions has this calculation built into it. The PyANP library, I believe, has it as well. For marginal analysis, so marginal, the reason I chose the name marginal analysis is from finance. You use marginal for derivative calculations. And so you can imagine I'm making this change with P going lower and P going higher than our resting P0 value. What is the instantaneous rate of change? So in other words, if I just make a tiny change and divide all of the resulting alternative scores by that small change, how fast is it changing there? If you want your left and right hand derivatives to match, use smart P0. That's exactly the definition. That's how smart P0 is defined, so that when you do the marginal, the derivative calculation, the left hand and the right hand derivatives match up. And the way I do this is I just go a little above P0 and divide by that delta, just like the numerical approximation for a derivative always does, and a little below. So what this tells you, this derivative calculation tells you, is for small changes in this priority, which node, if you look at it node by node, row by row, and look at the resulting changes, bigger numbers there mean that those nodes are more susceptible to small noise factors. So for those nodes, you probably should double check and refine any comparisons around it. So this is for that saving people time pairwise comparison situation. It lets you know also, if you were doing the public opinion thing, which you would look for things with positive derivative and go, okay, I need to make sure people think this node is more important so that I can make my political reform more popular. So marginal analysis is really great for that particular application. Okay, I've been talking a lot here. I'm going to take a break for a coffee sip and see if there are any questions. No?
How can I know which node is most influential without doing all these pairwise comparisons?
So you'll need to have, well, so let me take a step back. You could start with just your model set up with no pairwise comparisons at all and do an influence analysis. And what that would tell you, the ones that are most influential through this marginal analysis or influence analysis, whichever one, just look at the ones with the bigger numbers, and that would tell you the places to start pairwise comparing. So just pairwise compare things that involve that particular node, or those couple of nodes. Once you do that, you could repeat the process and do another marginal analysis and see if anything's changed. It probably won't. But if it does, you may have to do another couple of pairwise comparison sets. But it will definitely start off quicker, right? You could literally just start off with the structure of a model, do this marginal analysis and say, okay, where should I be pairwise comparing at all? Do a rudimentary one on those, do another marginal analysis, and say, okay, where should I refine now? Is it the same places or are there new places? The new numbers might cause it to have a slightly different result. Does that make sense?
Yeah, thanks.
Okay. Mm-hmm. Any other questions before I move on? So for perspective analysis, what I do is I push P really close to 1. Take the limit as P approaches 1. So what that means is I'm making that node the most important. So for instance, N2, pushing that one closer and closer to 1. What happens to my alternative scores? So it tells you from the perspective of this node, what alternatives are best. It turns out, I didn't put this on here, sometimes this matches with the column from the supermatrix for that node. Sometimes it doesn't. And that's a great, interesting research question. If anybody was interested in looking into that, you can reach out to me. I can give you some pointers on things to start on it. I've never had time to go off and do it. By the way, just so you all know, my day job is I do research and development for a company out of DC called Decision Lens that Thomas Sadi's sons and I founded ages ago now. So I'm not an academic. I'm an academic at heart, but I have a day job. So that's why I haven't pursued some research ideas on these things. Anyways, so that interesting question though of when sometimes it is, sometimes it isn't. Again, my feeling, my vague recollection is it's about a third of the time it's different in models and about 2/3 of the time it's the same. So for given a model, about 2/3 of the perspective columns analysis results will be the same as just the column from the supermatrix. But for about a third of them, it won't be. Why? I don't know. Okay, so rank analysis. This is similar to influence, except rather than pushing it up, like I said, for influence, remember I said we typically start at 1/2 and we go up to 3/4 and down to 1/4. For this, for rank analysis, I just start pushing along P higher and higher until the first time I get a rank change. And that distance I push, if it's a really short distance, that means that this node is really influential on rank. It causes a rank reversal quickly. If I have to push it a long ways out, it means the rank reversal happens. It's not very sensitive, or maybe I can push it all the way up and all the way down and it never has a rank reversal. That also happens. But the smaller the push, the more to get a rank reversal, the more influential that node is, that criteria is on the rank. Or you may say, okay, it changes the number 11 to the number 12th alternative. Who really cares, right? I mean, nobody probably, but you could specify, hey, I want to push this until the number 1 drops from being number 1 to number 2, because that's really interesting to me. And so you could do the same analysis, but rather than any rank change, you're looking for the number 1 alternative to drop. Which node causes rank reversal the first, earliest? So if you're thinking about this from a public opinion, if you have do your reform, don't do your reform, don't do your reform is winning, you say, okay, don't do your reform is winning. What node would I have to change? What node causes a rank reversal first? That's the place to focus for your, that's the place to focus changing people's opinion. So for instance, if it's an environmental reform, then maybe toxicity is one idea. And so making sure people have a good idea, public opinion about what toxicity means and how it affects people is where you need to be focusing in order to get your political reform through. All right, questions? All right. I guess I finished much quicker than I was expecting to on this. I have a couple other things I'll show you after the presentation is over here. So there's some resources available, and I'll show you what a couple of them look like in the last few minutes we have here. The ISAHP has a website, or has a GitHub repository that's also available as a website link as well. I need to put that in here. I have a Jupyter notebook that has many of these calculations in there. And then this is a link to my Python library that's freely available, open source. If you go to this link here, this is the ISAHP. If I go, let's see here, it's ishp.github.io/2022. This is what it looks like more as a website. So my presentation is available here. You can grab a copy of it. This Jupyter notebook. There is my research notebook, and then some of the calculations I did for the workshop are available here. So for those of you who are aren't familiar with Jupyter or Python, so Python is a programming language, and Jupyter is a way of interacting with the programming language that creates documents like this. So cancel here. Let me move you guys over so I can see what I'm trying to do here. Guess I gotta go this way. So it looks sort of like this when it's running on your computer. These little things here are markdowns. They're kind of like LaTeX stuff, if you've ever done that. Number sign means a heading. So it gives me this. And it's a way of sort of documenting code and coding at the same time. So the first part here is doing my initial imports, and then you can see my model. This is the unscaled supermatrix that gave rise to the scaled supermatrix that we use. So all of the calculations I did in the presentation are available here on this. If you don't have Jupyter installed, you can still look at this by going to the link in my presentation and just clicking on Sensitivity. So when you go to the main page here, you go to Workshops, Sensitivity, and the workshop.ipy notebook, NB. And it'll show you, not quite as pretty as the one I have on my running locally, but you can see what the code looks like. You could copy and paste it to your Python environment, etc. And here's where I defined my model at. And I have it printing out the result here. Scaling down, here's how I defined my function to scale down so I could see results. And if I run it over here, so what happens, so just so that to help you guys understand, the little gray boxes are Python code that's getting executed. When I hit Shift and Enter, it executes them. And the result is printed out below. Okay. So if you want any examples on that, they're available up there. In addition, my PyANP.org. Here's the PyANP landing page. It's got a lot of tutorials getting started. Here's the tutorial on ANP Row Sensitivity. It goes through how to start running stuff in Python. I even go so far, I believe on here, installing and getting started with Jupyter. So if you've never used Jupyter before and you've never used Python, I give a little overview of what it is and then installing. So all you have to do to find these resources is just go to pyanp.org, Python ANP library, pyanp.org. And it's got a bunch of tutorials up here. It'll get you started, how to use the AHP tree, how to do the limit calculations. So all the different limit matrix calculations I have are in there. Priority calculations, row sensitivity. There's a programmer's reference, if you feel like looking at the programmer's reference, etc. Excuse me. Okay, so that's how you get started using PyANP to do any of these sorts of analyses. So you don't have to do them all by hand the way I showed you in the presentation. I did that just so that people would understand how it works, and then let the computers do the annoying, tedious stuff. Okay, I think unless there's something about what's on my screen here, I will stop sharing screen. All right, are there any questions for the end of the talk here?
Hey, Bill, this is Marcel. I've got a crazy question for you, and it's not well formed yet, but
Okay.
I'll just put it out there to see. When you went to your Jupyter notebook in Python library, this brought it up to mind. I just emailed Luis this question yesterday too, but not with respect to sensitivity. So I'm working on a project with the meta governance project, looking at use cases for DAOs, decentralized autonomous organizations. And I wonder, is there a way for us to put this sensitivity analysis onto a blockchain with smart contracts for decentralized governance? And when you were talking about policy, this is what was making me think about this, right? Because in group governance settings, where we're trying to get more contribution, is there a way for individuals to contribute to the sensitivity analysis so that decision makers, or in particular collaborative decision making, can be improved? I know that's kind of out of left field, but and if you don't have an answer now, then we can always get offline and touch base on it as well.
Yeah, actually, I could see a use for that. So one idea, so you have a model that's going to sort of that influences a decision, right? And you want people to have a quick way to put an input in. And what you could do is have something, let's just say you have your list of criteria, okay? And you go, okay, people, I want you to tell me what's the most important thing to you in this. And they'll say, they don't get to tell you how much. They just tell you yes or no on each, on one, pick a node. And then for that node, you could do a little delta up on its priority. You could count up the number of people who do it. So go across to all of them. Whoever gets the most bang up. Whoever gets the least is going to get a bang down. And make an adjustment to your model that way. And people could have input without having to input 1,000 bloody pairwise comparisons, right? They just tell you what's the most important criteria to them. You could take all of that information in, totally do it. I didn't put it up on the presentation because I don't want spam mail, but if you want to reach me, probably the best one is my personal email, which is easy for me to say and for you to write down. It's wjladams@mac.com, MAC like Macintosh computers, mac.com. WJLADAMS. William James Lewis Adams, WJL Adams @mac.com. If you have further questions, or Marcel, with this particular thing, we could definitely come up with a model to do that.
Yeah.
And there'd just be a few extra calculations. just reach out to me. We can get started on that.
It
That'd be
definitely
cool.
will. Definitely will, Bill. I was talking with some folks at the MetaGov project the other day, and when this idea initially came to my head, and they seem pretty interested in it. So I'll connect with you.
Okay.
Thanks.
I'm also on Twitter at WJL Adams as well. If you want to just DM me through that, you can reach me that way as well.
Perfect. Thank you.
Mm-hmm. Any further questions?
This was excellent question, Marcel.
It was. Yes, application I would never have thought of.
Yeah.
Thanks. It's not often I get that kind of compliment. I'll take it.
Excellent. So definitely reach out to me if you all have any further follow-ups. If you have research questions, if you have a research project that you need to do this kind of calculation on, I can point you to the right resources to get you set up. You have to have a little patience with me because I do have a day job. Unfortunately, research on this isn't my primary position, but I would be willing. I'm definitely willing to help. And if you didn't write my email address down, Elena has it, and Nirong has it probably as well. So they can get you in contact with me as well. Oh, I'm also WJL Adams on Skype, but I am almost never on there. So Elena knows that. Okay. Well, I thank you all for your time, and just reach out to me if you have questions.
Thank you so much for the nice lecture.
Thank you ever so much.
Yeah.
Thank you all very much.
Thank you so much, Bea.